example number 315. So this example 315 on page 124. Right? We want to replace this system of forces, including 1, 2, 3 force, with a resultant at point O. So in fact, the question is, it says simplify the system of forces at point O. So you end up with one resultant force and one resultant moment. This is the objective of simplification, right? So what should I do for resultant force? Resultant force, right, is a vector in 2D. So how many components is that? It has 2. Resultant force has resultant force in the X and resultant force in the Y. So I should compute these 2 components. And also for the moment, I only have one component because it's 2D. The moment is always in Z. It's either outward or inward, right? So I pretty much know what to do right now. So let's go find FRX, the X component of resultant force. Let's start with this guy. Negative 200. You go to this, plus 200. X component of that is going to be 500, 3 over 5, positive, and there is no other force in the X component. That's pretty much all we have, right? Now for Y component. This one is 0. It doesn't have any contribution to Y. 0, right? This one, positive 500, 4 over 5. Right? Positive. And that one, negative 750. Right? So I'm pretty much done for force. Now moment, resultant moment around O. Right? Let's start with this one. This one, we have a 3-step for every single force. We have a 3-step procedure. Break it down, move it, compute it, right? This one is already in the Y direction, so we don't, like this, we don't need to break it into X and Y, right? Already in Y. So what's the moment arm? And it's already moved. You see here, this is your arm, so it's already orthogonal. If it was right here, you should have moved it down, right? So the first 2 steps, you don't do anything. So what's the moment arm? 1.25 times 750. Positive or negative?
Negative.
Thank you. Now we go to this one, right? So this one has X and Y component. So the X component is 500, 3 over 5. Where should I move it? All the way back here. So what's the moment arm? From here to here. 1. So 1 times the value of force. 500, 3 over 5. Positive or negative?
Negative.
Thank you, negative. And this one, the Y component, is, let's first explain it actually. So, step 1, break it down. Well, I'll break it Y component. 500, 4 over 5. Now move it. Where should I move it?
Down.
Down, right here. So what's the moment arm?
2.5.
From here to here. 1.25 plus 1.25, 2.5. Right? So moment arm 2.5 times the value of force component, which is 500, 4 over 5. Positive or negative?
Positive.
Positive, perfect, thank you. Now, right here, look, in the force equation, they cancel out each other. You see that? Negative 200, positive 200. Why? Because this is a couple moment. You remember last class? couple moment is generated by two forces exactly equal but opposite direction. And we proved that when you have a couple moment, you don't do anything with the force equation. Even if you do it, they cancel out. You see 200 negative 200. They will add to the moment equation because they have purely rotational effect. They don't pull or push. They cancel out. They have purely rotational effect. So they will add to the moment equation. So don't say, well, they were canceling out in their force equation, so they also cancel out here in the moment. Don't say that. They are coupled moment. They add to the moment equation, right? So the way we add it to the moment equation is we say the value of force 200 times the distance between them. The normal distance between them is 1. So you expect 200 times 1, which is 200, to be added to moment equation, right? But right now, let's just do it manually, like the way we did it for forces, using 3-step procedure, right? So the first step, break it down, is already in the x component, right? The second step, move it. Where should I move it? Here or this way? Back to the, here, right? So what's the moment arm? 0.5. So this one, 0.5 times value of force 200, positive or negative?
Positive.
Positive, right? Now go to this one. Move it. Where should I move it?
Back.
Back. So what's the moment arm?
0.5.
0.5 times
200.
positive or negative?
Negative. Positive.
Positive. That's the point. Take your right hand. This is your R from here to here. Goes to R, then the palm would show the force 200, and then the thumb is positive K. So as you can see here, if you factor out the 200 Newton, 1 plus 1, half plus half is 1. So 1 times 200, that's exactly what you expected from the concept of couple moment. The value of couple moment was the value of force multiplied by the distance between them, right? So you really expected the 200 to be added to the equation, and as you can see manually we did it with the method of molar forces, and we get 200 added to the equation, right? So that's all you get, right? So let's do this simplification. The numerics, let's put it in the calculator. 500 over 500, 300, 200, 500, 200. So that's going to be 300, right? This one is negative 350. And this one is equal to, put it in the calculator. Negative 37.5. Negative, come on, 37.5. Right? So that's the value of moment. This is the y component of force, this is the x component of force. So I'm ready to replace all these forces, no matter how many forces and moment you have in the system. I'm now ready to replace it with one force and one moment at that particular point. And this is called simplification. This is this section, simplified, right? So let's do that. So I go, let's try it one more time. So this is my on here. So instead of always staying here, I put a resultant, F resultant, right? And then I put a moment. It's negative, so it goes this way. So the value of moment, M resultant, is 37.5, and resultant force, its value is equal to, well, its value is equal to the square root of 300 plus 350 squared. Put it in the calculator. So square root of 300 plus 350. 461. This is or 61. 461, right? So, in fact, let's just copy this. 461, right? And you also have this angle. How do you find this angle? Well, if you have x and y component of resultant force, then that angle, this angle, is theta, right? Theta is r tangent. The y component of resultant force divided by x component of resultant force. So when we have y, x and y, r tangent x over y, the value of that is the value of theta, this angle from here to here. This has a positive x component. Here, if you project it, the x component is 300, you see here. And the y component is 3, this is 350. So the angle can be obtained r tangent y over x component, right? So we ended up with one force and one moment. No matter how many forces and moments we have in the original system, we will end up with one force and one moment, right? Now, there is another section in the book. It's called further. It's right here. Further simplification. Further simplification of force moment system. That means that you can further simplify these two into one. So right now we have a force and a moment, right? We can simplify it into just one single force. How can I do that? Well, so far we could move force along line of action, right? Without any change, without any difference. Because we proved it. The moment equation will be balanced. There would be no change if you move the force along line of action, right? Now, if we move a force sideways, right? Sideways, just perpendicular to this angle theta, right? Such that this single force by itself can generate this moment. If we could do that, then I can just ignore this moment, and then at the end I will have just one force at a particular distance acting along a particular line that also generates that resulting moment effect. So I can further simplify the system with just one force instead of one force and moment, right? So let's do that. At what distance should I move? Let's draw it here. At what distance should I move this 461 Newton force sideways? Means that along this line, for example here. At what distance d should I move that such that I get the same amount of moment that I already have here? So I can just delete this moment and just have the single force acting at that particular distance. So what is that distance? Is there anyone that can solve it? Yeah. That's it.
Something like that.
That's right. Perfect. Thank you. We want to Your name again?
Derek, it's spelled weird.
Yeah, there you go. Oh, okay. All right, so what he wrote here is another expression for moment. So D times 461 is the moment generated by the force. Why? Because the value of force is 461 times this distance that we shift this force, right? What moment is generated? D times 461. So 461 times D, this moment should be equal to what? The moment that you already have here. What's that? 37.5. So if you solve, this should be equal to 37.5. If you solve for D, D is equal to 37.5 divided by 461, which is 0.08 meters, right? Almost 80 millimeters, right? So in that case, I can further simplify this force. I no longer need a moment because my force can generate that equal moment, right? So I will end up with just one single force. Its value is equal to 461, and its location is almost 80 millimeter from point O. And you already have this angle theta. So this angle is also theta. How do you compute it? Arctangent and forward. So you can exactly determine one force at the end of the day, one force that is responsible to be equal for this distribution of force and moment. This is the most simplified form of the system. One force with a particular distance with respect to that point can generate all the force and moment system here. This is like a balancing the system, right? We replace everything with just one single force that can generate not only the effect of forces but also the effect of rotation, right? Now let's go to another example, 3D example at page 125. Example, we have two forces and one moment. Look, when you see this curved arrowhead, this is moment. This is not the force vector. So similar to this guy, it's like a couple moment. So all you do, similar to this guy, it's like a couple moment, right? All you do, you add it to the moment equation. Because if you add it to the force equation, they will cancel out. Right? So you don't even bother, you just add it to the moment equation, right? So I want to replace this system force and moment with just one single force and one single moment at point O, and this is my point O. Solution. Go ahead and solve it. So I write F resultant x component is equal to sum of all the x component. So you find the resultant force, you find the resultant moment with respect to O, then you put force, resultant moment vector 2, and you get rid of the rest of it. This is the procedure. So the resultant force x component would be, let's start with this guy. Does this have any contribution to the x component?
No.
No, z, right? This is just a moment. You don't even add it to the force component, right? So the only thing that remains is this guy, right? So yes, this one has an x and y components. Let's decompose it. This guy, this is the y component. You see, it goes around y. And this one is the x component, which goes in the negative x, right? So all I need to find is to find this angle theta. Because I have the value. If I have that angle theta, I can find the x and y component. So what's the value of theta? If you come to this triangle, the value of theta is the same here. Because that force, this force is going through the center. The line of the force is going to the center, to this z-axis. You see, the drawing is not perfect. The drawing is not very proportional. That's the reason I say always bring your book with you, because the drawings are not always good. So if you look at the book, this force is going through the z-axis, so that theta is the same, right? So what is that theta?
56.3.
Tangent of theta is equal to, now in this triangle, you see, consider that triangle. Tangent theta is what in that triangle?
0.15 over 0.1.
The front, 0.15 over the side, 0.1, right? So, theta is arc tangent 0.15 over 0.1. Put it in the calculator. Did you put it in the calculator? So it's 56.3 degrees. Now I have the theta, right? Now let's go ahead and write the resultant force in the x component. As I said before, this has nothing to do with the force, it's just a moment, so you don't add it to the force equation. This one is in z, nothing with the x direction. This one is in a y, so this one is in x. Positive or negative?
Negative.
Negative 300 times sine 56.3. Right? Now, I'm done with the x direction. Now let's go to the y direction. F resultant y direction. Right? Again, start with this. It has nothing to do with the force. This is a moment. This one is in a z direction. Right? This one is in an x direction. And the only thing remains is this. So I should write positive 300 times cosine 56.3. Right? Now let's go to the moment. Well, in fact, because it's 3D, before I go to the moment, I should find the z component of resultant force. Right? What's the z component? Again, starting with this has nothing to do with the force. Ignore it.
It's negative 800.
Negative 800. This guy is purely in the xy plane, right? It just shifted a little bit up, right? So it has no contribution in z. So that's all. All I have in the z direction is 800 negative. See that? Now, these are the component of force. My resultant force vector. You see Fr with a rho on top of it. Now let's go to the moment. Resultant moment vector. So you have x, y, z component. Mrx, Mry, Mrz. So let's fill it out. Find the moment with respect to point O about the x-axis, the resultant moment. Let's just start with this guy.
0.
0, it goes through that, right? Now let's just start with this. This one. Then you ask the question, can it generate the rotation about the x-axis? It's parallel, right? So you ignore it, you go to the next one. What about this guy? Again, you ask the question, can you generate any rotational effect about the x-axis? A torque? Yeah. Then you compute it. Then you go to a step 2. Step 2, move it. Where should I move it? Here or here?
Back.
Back, yeah, here. So what's the moment arm? From here to the x-axis.
1.
Which is here, yeah, right? Which is here. So it's all, that distance is just 1, right? So you say 1 times this component, right? This component is 300 cosine. Angle is 56.3. Positive or negative?
Negative.
Negative. What else? We have a couple moment that will be added directly. You don't need a distance or moment arm for this because it's a moment. Like that. You see, 200 times 1 will be added to the equation. You see 200 times, factor out 200 times 1. Half plus half is 1. Directly added to equation. There is no moment arm. Right? So, but look, this guy is either in the Z or in the Y. It has nothing to X because it's in the ZY axis, ZY plane, right? It has no contribution to the X. So that's the reason we ignore it. This one goes through X, so the moment is 0. This one is parallel, so the moment is 0. So the only thing that remains is this guy, which we did it. So that's all. So you can check mark it. We're done here, right? Now let's go to the same point, but take axis Y for moment computation, right? Let's just start with this. Let's do it very quickly. 0.
Point.
This one. We are doing this axis.
Negative 1 times 300.
Sine 56.3.
Look, this one and this axis.
Oh, it's parallel.
Yeah, always ask the question, can this generate a rotation about this axis?
No.
Well, as you can see, it can generate a rotation about x-axis or z-axis like that, right? But it cannot generate a rotation about y because it's parallel, right? So this one is 0, right? What about this guy?
Negative 1.
Negative 1,
300 sine.
300
Sine.
sine 56.3. So I'm done with this guy. I'm done with this. Now let's go to this. What's the component of this guy in the y direction?
500 3/5.
500,
4 bits.
4/5.
4, 3, hold on, 4 over 3. Yeah. Positive or negative? 4 over 3. Yeah. Positive or negative?
Positive.
You see, this is in this direction. And the positive is this direction. So, negative. That's all. For the couple moment, for this moment, you don't need the moment arm. You need a moment arm for forces, but not for moment. This will directly be added to your moment equation. Right? So let's find moment about z-axis. The same procedure. Let's just start with this guy. 0. Why? Because it's not only go through the z-axis, but it's parallel. So two conditions. 0 times 0. So this is 0. What about this guy?
500
Uh-huh.
3/5.
Positive or negative? Positive. You see? The tip, this arrowhead, this is here. So when you project it, go up. If this was going down, the projection would give you a negative. But this is positive. right? So we got rid of these two guys. Now let's solve this. 3-step procedure. We have already done the first step. Break it down. Decompose it. Step 2, move it. This guy, where should I move it? All the way back here. So what's the moment R?
0.15.
From here to here, 0.15. Time?
300.
Time? 300 what?
Sine. Or
300.
We are moving this cosine. Yeah, 300 cosine 56.3. Positive or negative? Negative. You see that? R cross F, negative. Now, go to the other component, move it. Where should I move this guy? This way or this way? Back, here. So the moment R
0.1.
is 0.1. 0.1 times 300
Sine 56.
sine 56.3. Positive or negative?
Positive.
Positive. That's it. So at the end, I have one. This is not 3 vector. This is just one. This is the x, y, z component, Cartesian form. One moment and one force. So no matter how many forces you have or moments, you can just eliminate all and put here one force like that, F resultant, and one moment. So moment has x, y negative, so it goes that way, and z positive. Maybe. So, like that. M resultant. You see? We can put a resultant force, you have all the components. You can perfectly draw it, right? Because you have numerical value of all components. You can find also the angles, alpha, beta, gamma, right? Because you have the components. That's enough to find the angles too, right? Similarly for a moment, you have all the components. You can find the angles, you can find everything. So you can just put one moment, one force, and get rid of all this loading on the system. There you go. That's the simplified version. And the value of FRMR is given here. Okay? Now let's talk about distributed loads. That's okay, I have 10 minutes to talk about distributed loads. So far, what we have seen so far is just point forces. You see? A force that is acting on a single point. So far, right? And we could say that the analysis was way simpler than any other thing. Just one moment R, you can compute the moment, you can decompose the X, Y, Z, because it's just a single point force, right? But look, in the actual nature, everything is distributed load. How come? For example, I'm standing here, right? I'm applying a force on the floor here, right? So I'm not applying, if this is me, right? I'm standing here, right? I'm applying my half of weight on the earth with this feet, half with the other one. If I stand like perfectly balanced like this, half goes with this leg and the other one with the other leg, right? But look, I'm not applying, look at this point. Now we want to talk about the detail of this contact point. I am not applying this force at the one single molecule on the surface of the floor. I'm applying on an area, so this kind of distributed load, right? So if I can draw this like zoom 10, zoom 50, 50x, right? Then I would have something like that, and this is my shoes, right? So I have some significant amount of load that I'm applying to the surface of the earth, and this is, let's say this is the floor, right? So I'm applying a bigger force here at some point here, right? And also a bigger force somewhere here, right? And then a smaller force here, a very small force here, and almost zero here, right? And then when you come back, a smaller force here, and a smaller force here, and here it's almost zero, because this is not in contact with the earth. You see that? And here I have a bigger force, but very small at the end, right? And very small here. So your force is kind of distributed like that. You see? If you draw the force distribution, it's kind of infinite number of point forces. Because you know my shoe sole has an infinite number of contact points with the floor. Right? Each one is like a molecular level. If you do zoom like 1 million or 1 billion, you will still see a distributed load. Each molecule has a different loading on it. So in fact, the actual physics is pretty complicated. All we want to do, engineers, we want to simplify. We want to replace, we want to get rid of this guy, right? We want to get rid of this guy and replace it with one single load that goes at a particular point. It acts as, we'll talk about that, at a particular point. Because what? If I have just one single load instead of distributed load, I can do all the analysis I've done so far. I can reuse all the technology I have developed so far. And I can analyze the system, right? So that's what we're going to talk today, how to replace a distributed load with a single load and just eliminate the distributed load, right? So here is the procedure. If you have a distributed load, then step one, find the centroid, geometric center of the given distributed load. To compute the area under the distributed load. 3. So this gives you the value of the load. The area under the distributed load, it gives you the effective value of the load or value of point load that you want to replace it. Point load. Alright? 3, replace, this is the important thing, replace the distributed load with the computed point load acting at a centroid. Well, in this example, we have a very complicated profile. How do you find the centroid of this complicated profile? We will talk later when we go to the centroids and moment of inertia. You have to use integration to find the centroid, right? But look, all the forces we do, not all, most of the forces we do in this course is simply either uniform. So let's consider this. We have a force like that, a uniform, or a just triangular, right? Loads that we have in this course, it's either uniform or triangle. You may end up with trapezoidal, but you can break it down into uniform and a triangle. We'll solve some example of that. So the step number one, find the centroid, is pretty easy. What's the centroid of this guy? It's just somewhere here, middle, right? What about this guy? If this is h, the height, right, is 1/3 is the point here. It's closer to the base, and this distance is 1/3 of h, right? That's all. So it's pretty easy to memorize. From the base is 1/3 of the height. It's not 1/3, it's 1/3 of the height. If this was 0.5, it's 1/3 of 0.5. Don't forget that. It's not always 1/3. Sometimes students make that mistake. So the step number one is pretty easy as long as you have loading like this, right? What about the step two? This one is even easier. What's the area of this guy? If this is h, and this is a b, the area is?
1/2 base times height.
No, this is
Based on what?
based on height. It's uniform. You see this is a rectangle. 1/2 times based on height is this guy, the triangle, right? So the area is pretty easy too, right? So all you do is say, if you give me this distributed load, the first thing before I compute the resultant moment, the first thing before I do analysis, the first thing I do, I just get rid of this guy and replace it with one single load going through the geometric center. So I put one single point load here, right? What's the value of this? The area, B times H. And it's going through the centroid. And then I get rid of it. I no longer have a distributed load. So I have my single load. Its value will be BH. Whatever numerical is given to you, B times H. And it acting as a centroid. And same here. So you can just compute the area. That's going to be the value of the force, put it at the centroid, and eliminate. Don't forget to eliminate the distributed load. Because if you don't eliminate it, you have to consider it in the moment computation. Now let me give you an example. That's what I did here. find the resultant moment MR with respect to point O. So basically, let's say this is a beam. Let's say this is the roof of your building, right? And there is a force here. Let's say one of these I-beams is attached to something. And then there is some snow. There is some snow here. Let's use blue color. There is some snow. Here you have more snow. And here you have a smaller snow. Or some loads. Right? You have some loads here. Whatever. Then you can estimate the loading with the distributed triangular. Because here you have more loading than here. Now I want to find the resultant moment of a load. I can immediately use this using the technology I had, 3 steps, right? But what about this? I have a distributed load. So the first thing I do, procedure, get rid of the distributed load. Replace it with the point load. So what's the geometric center of this guy? It's 1/3 of the height. The height is 1. So 1/3 of 1 from the base, from here. You see? So this is 1/3. So what is this distance? From here to here. 2/3. Right? So that's the location of centroid. That's step 1. Find the centroid. 2. Compute the area under the load. What's the area under this load? The height is 5 kilonewton per meter. The bottom is 1 meter. So what's the area? The area is half of base times height, 5K,
2.5.
which is 2.5 kilonewton. So this is the value of single load that we want to replace it. So where should I put it? Here. So I get rid of this. You see? There you go. And I put it here. Don't forget we can move force along line of action. So I can bring it down a little bit. So I get 2.5 K at the location 2/3 from this point. So the resultant moment is M resultant is equal to resultant moment of this, which is 1 plus which is 1 plus
2/3.
1 plus 2/3 times 2.5 K. Positive or negative?
Negative.
Negative. Then we go to the next one. This one, you have to do 3 steps. Decompose, move, compute the moment. So you have 2K times cosine 30 times 2 plus 1 plus 1. 4. Right? And then 2K sine 30, this component. What happens to this component?
0.
0, it goes through the point. So that's it. Plus 2K cosine 30 times 4. So that's the resultant moment. You see? Now we can analyze systems that they have distributed loads as well, like this. Now we're ready to do free body diagrams. All right?